Hello everyone. Today we are going to analyze a simply supported beam when it carries an eccentric point load W. Let us keep the left end as A, right end as B, and the point under the load as C. Let us keep the distance between A to C as A and C to B as B, and let us keep the span of the beam as L. To find RA, let us take moment about B. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. RA is acting in the clockwise direction, so it will be positive and the distance is L. So RA into L. The load W is acting in the anti-clockwise direction, so it will be negative and the distance is B. For RA, we will get WB upon L. To find RB, let us take moment about A. In this case, we have to follow left hand side rule. RB is acting in the anti-clockwise direction, so it will be positive and the distance is L, so RB into L. This load is acting in the clockwise direction, so it will be negative and the distance is A. For RB, we will get WA upon L. Alternatively, using this rule, we can find RB. RA and RB are acting upwards, so both of them are positive. W is acting downwards, so it will be negative. We can take these two terms on the other side. We can take W outside. For these two terms, we can take LCM. In this way, for RB, we will get WA upon L. Using the right hand side rule, we can find the shear force at just left of A, right of A, and at just left of C. Shear force at just left of A will be 0 and at just right of A will be RA, which is acting upwards, so it will be positive. Let us find the shear force at just left of C. Up to left of C, we have only this. So here also we will have the same shear force WB upon L. Using the left hand side rule, we can find the shear force at just right of B, left of B, and at just right of C. Shear force at just right of B will be 0 and at just left of B will be RB, which is acting upwards, so it will be negative. Let us find the shear force at just right of C. Up to C we have only this. So here also we will have the same shear force minus WA upon L. Here you can see the shear force diagram. We know that in the simply supported ends A and B, the moment will be 0. From the point A, I am going to find the moment at C. In this case, we have to follow right hand side rule. RA is acting in the clockwise direction, so it will be positive, and the distance up to C is A. WB upon L into A, we will get WAB upon L. Here you can see the bending moment diagram. Now using the Macaulay's method, we are going to make expressions for the slope and deflection. For that we have to make sections. In this beam there are two different parts, AC and CB. So we have to make two sections. You can see that I have made two sections, one in AC and one in CB. I have made both of the sections at a distance of x. From the point A, I am going to find the moment about the sections from the point A. In this case, we have to follow right hand side rule. RA is acting in the clockwise direction, so it will be positive and the distance is x. So RA into x. The point load is acting in the anti-clockwise direction, so it will be negative. For this load, we have to take this distance. This distance will be x minus A. We can equate the moment to EI d square y upon dx square. On both of the sides, we have to integrate. When we integrate d square y upon dx square, we will get dy upon dx. Using this formula, we can integrate x. That will be x square upon 2. C1 is the constant. To integrate x minus a, we can use this formula. We will get this. 2 into L, it will be 2L. One more time, we have to integrate on both of the sides. When we integrate dy upon dx, it will be y. When we integrate x square, it will be x cube upon 3. In this term, there is no x, so we have to multiply x, that is the integration. C2 is the new constant. When we integrate this, we will get this. 2L into 3, it will be 6L. 2 into 3 it will be 6. Now let us apply the boundary conditions. In the point A there is a vertical support. If there is a vertical support there will be no deflection. At A x is 0. So when x is 0 the deflection y will be 0. We can apply both of them in this equation. When we do that we should not consider this because this term is only applicable when x is more than a. When we apply these it will be 0. Here it will be 0. It will be 0. In this way for C2 we will get 0. In the point B also there is a vertical support. So when x is L the deflection y will be 0. In this one let us apply these and C2. Now we have to take this term also. We can eliminate L. Here it will be L square. We can take these two terms on the other side. L minus A is B. We can take WB upon 6 outside and then we can take LCM. From here we can take a negative sign outside. So it will be L square minus B square. For C1 we will get this. First let us take the slope equation. In the slope equation let us apply the expression for C1. From these two terms we can take a WB upon 2L outside and let us take EI on the other side, so it will come in the denominator. For these two terms we can take LCM. 2 into 3 it will be 6. Let us keep this equation as number 1. Let us take this. Using this expression we can find the slope at any point. When x varies from 0 to a, then we need to take the whole. This expression is used to find the slope at any point when x varies from a to L. To find the slope in the point A, in this one instead of x we have to apply 0. For theta A we will get this expression. To find the slope in the point B, in this expression instead of x we have to apply L. 3L square minus L square it will be 2L square. L minus A is B. We can multiply this term with 3L upon 3L. Then we can take WB upon 6EIL outside. Here we will have 3LB. B is L minus A. For this we can apply A minus B the whole square. We know the formula A square minus 2AB plus B square. Using that formula we will get this. We can eliminate 3L square minus 3L square. 3AL minus 2AL it is AL. We can take A outside. We know the formula A square minus B square. A plus B into A minus B. Using the formula we can write this as L square minus A square. So this is the expression to find the slope in the point B. To find the slope under the point load, in this expression instead of x we have to apply A. We know that L is A plus B. Then we can use A plus B the whole square formula and then we have to multiply with the negative sign so that we will get this. We can eliminate B square. 3A square minus A square it will be 2A square. From here we can take 2A outside. 2 upon 6 it is 1 upon 3. For the slope under the point load we will have this expression. Now we have to find the location where the maximum deflection occurs. The maximum deflection occurs on the large segment AC. When there is maximum deflection the slope will be 0. Let us take this and we have to equate that to 0. We can take this term on the other side. It will be 0 into 6EIL upon WB. When we multiply any value with 0 it will be 0. We can take these two terms on the other side and we can take 3 on the other side. It will come in the denominator. For x we will get this. Now we are going to find the maximum slope. For theta A we have got this expression. We can multiply WB with this so that we will get this. For theta A to be maximum, the differentiation of theta A with respect to B will be 0. For B the differentiation will be 1. So here minus WL square. For BQ the differentiation will be 3B square. So here W into 3B square. We can take W outside and we can take W upon 6LEI on the other side. So it will become 0. For B square we will get this. So for B we will get this. A will be L minus this. So there will be maximum slope of A when A is this value. In this one, for b, let us apply L upon root 3. Here we have b square. B square is L square upon 3. After simplifying, for the maximum slope at a, we will get this. In the similar way, we can find the maximum slope at b. We will get the same value. So this step is not required. This is the maximum slope we know. Now let us take the deflection equation. In that, let us apply the values of C1 and C2 so that we will get this. We can take EI on the other side. It will come in the denominator. From these two, we can take minus WBX upon 6L outside. Let us take this. This is the expression to find the deflection at any point when x varies from 0 to a. Let us select the whole. This expression is used to find the deflection at any point when x varies from a to L. You can see that this expression is a little complicated and it is difficult to remember. So we can have a shortcut. We can find the deflection from A to C and from B to C. So we have to make the first section from the point A and the next section from the point B. This one we have derived. From B to C, to find the deflection at any point, instead of B, we have to just apply A. So this expression is applicable from A to C, that is when x varies from 0 to A. And this expression is applicable from the point B to C, that is when x varies from 0 to B. Now using this expression, we can find the maximum deflection and the deflection under the point load. To find the deflection under the point load, instead of x, we have to apply A. So in this expression, instead of x, I have applied A. L is A plus B. Then we can use the formula for A plus B the whole square, which is A square plus 2AB plus B square. We can eliminate these two and these two. We can eliminate 2. Here it will be 3. B into B, B square. A into A, it is A square. For the deflection, we will get a negative expression. That means the deflection is downwards. To find the deflection in the center, in this, instead of x, we have to apply L upon 2. X square will be L square upon 4. When we add these two, we will get 3L square upon 4. For these two terms, we can take LCM. 4 is the LCM. 12 into 4, it will be 48. For the deflection in the center, we will get a negative expression. That means the deflection occurs downwards. Now let us find the maximum deflection. We have got the expression for the location of the maximum deflection. In this expression, instead of x, we have to apply that. For x, I have applied here. And here it is x square. When we square this, we will get to this. Then we can take LCM. 3 is the LCM. 6 into 3, it is 18. Minus L square plus 3L square, it is 2L square. B square minus 3B square, it is minus 2B square. From these two, we can take 2 outside and then we can eliminate 2 and here it will be 9. We can take root 3 outside. We know that root of x will be equal to x power 1 upon 2. So we can write root of L square minus B square as L square minus B square power 1 upon 2. And we know that a power m into a power n is equal to a power m plus n. In this way we can add these two. Here the power is 1. 1 upon 2 plus 1, it will be 3 by 2. So that we will get this. So this is the expression for the maximum deflection, and this is only applicable when A is equal or greater than B. Alternatively, we can make another expression. Instead of L, we have to apply A plus B. Then we have to use the A plus B the whole square formula. We can eliminate B square. So this is also an expression for the maximum deflection. We have got a negative expression. That means the deflection occurs downwards. We can remove the negative sign from the deflection. Here you can see the elastic curve. Now we are going to end this session. Thank you for watching this video.